line integrals. Line integrals. Here we seek to understand and use this concept of a piecewise smooth curve to be able to write and evaluate a line integral. We can discuss the line integral in terms of vector notation, or you can discuss line integrals in terms of differential form. So first, we begin by talking about a piecewise smooth curve. Here, let R of t represent the curve. This curve here is represented in the plane. R of t is equal to x of ti plus y of tj on some interval for t between a and b. R is said to be smooth when the partial derivatives dx, dt, and dy dt are continuous on the closed interval and not simultaneously zero on the open interval from a to b. That is, that they're not both, the partials are not zero on the open interval. So whether it's the plane or in the space, the same argument for smoothness. You want the partial derivatives to exist, to be continuous. The line integral, when we define it, is defined on this piecewise smooth curve. So here, recall from calculus that the integral from a to b of f of x dx integrates the area under the curve of f of x. The double integral here over the region of f of x y dA, we're integrating a region, a function over a region. The line integral is the integral by which you investigate the energy along a certain path that the curve itself exhibits or generates. And so as a particle moves along a certain path, you want to calculate whether it's the vector field, you calculate the energy flow along that path with respect to the function. So here, this line integral is calculated. Think in the sense that the line integral is very similar to the arc length. So you can examine the arc length of a curve, but here in the space, we don't talk about the arc length. Here we talk about the integral along that particular curve or path, and so we call it the line integral. The term is misleading, line, because it's really a curve and you're moving along that curve on a path. The definition of the line integral of f is defined on a region containing a smooth curve C. If C is smooth, that means its partial derivatives are continuous. Then the line integral of f along C is given here by the limit as the partition goes to 0 of the summation of a function, whether it's f of xy or f of xyz, with respect to the change in the surface, or here this little s, meaning I'm thinking section 15.6, but this is 15.2. This is the change in s. Here s sub I represents little arc lengths. And so you're calculating the sums of those, and provided the limit exists, we say that we have the line integral. Now you can look at the line integral here in terms of how to evaluate them. How do we actually get it? So this line integral over the curve of f of xy or f of xyz ds equals here to this integral, this definite integral, where f is continuous on a smooth curve C. C is given by R of t. T is defined between a and b. Now ds, this ds here is, look, it's the arc length times dt. It's stated right here for you. So this ds is the norm of r prime of t dt. So with that in mind, let's see if we can here work some problems, evaluate the line integral along the given path. So we need to find a couple of things. Well, the first thing is we need r prime of t. because understand that this becomes the line integral over here. Now the region, I better back up, over the curve of xy, that ds becomes the norm of r prime of t dt. And the x and the y must be represented in terms of r of t. And I'll show you that in just a second. So here, the derivative of r is 4i plus 3j. Now we need the norm. Oh, too much. Crap. Hot dog. So this is the square root of 4 squared plus 3 squared, and that gives us 5. So now here, notice that based on the definition, r of t is defined as x of ti plus y of tj. So if that's the case, then here x is equal to 4t and y is equal to 3t. Do you see that? So here x of t, think about that as x, is equal to 4t. And y, which is the same thing as y of t, is equal to 3t. So this integral up above is this line integral over the curve of xy ds. This is the integral from 0 to 1, where x is 4t, y, this is x times y is 3t, and then times here ds. ds is the norm of r prime dt. Well, we have the norm of r prime, that's 5, then here times dt. So we get 60 times the integral from 0 to 1 of t squared dt. So that gives us 60 times t cubed divided by 3. Evaluated from 0 to 1. And that gives us 20 here times 1. And that's just 20. What about this one? We need r prime of t. So this is cosine ti plus or negative sine. So just say minus sine tj. The derivative of 2 is 0. So what about the norm of r prime of t? It's just equal to 1 cosine squared t plus negative sine squared t. That's written kind of funny. Plus parentheses negative sine t to be squared. Well, it's equal to 1. Now, do you see that x is equal to sine t? Y is equal to cosine t, and z is equal to 2. So that's the case. We have the integral here from 0 to power over 2 of the function. The function here is x squared plus y squared plus z squared. So x squared would be sine squared t plus y squared, that's cosine squared, t, then plus z squared, that's 2 squared. And then it's times this norm of r prime, which is 1 dt. I tell you what. I just can't write a 2 for some reason. You get it, right? So sine squared plus cosine squared is 1, and then 1 plus 4 is 5, times the integral from 0 to the power of 2 dt. So we get 5t evaluated from 0 to the power of 2. And that gives us 5 pi over 2. Now with this problem, they don't tell us what r is, what the path is. Find a parameterization of the path C, and part B, evaluate. So first we need to represent r of t. Well, this, it says it's a line segment starts at 0, then it goes to 1 comma 1. So this is a line segment. Notice that x is equal to y. And you can build the equation of the line you want, but hopefully you see here that this is y equal to x, right? So that's y equal to x. I need to build r of t where I have some term here that represents x plus some term here that represents y. Well, and it has to be in terms of t. Well, if y equal to x, well, it's the same thing. We just set that equal to t. So r of t is equal to ti plus tj, because x is assigned to t, y is also assigned to t. How x moves, y moves. So x equal to y equal to t. So if that's the case, remember we need r prime of t. Well, that gives us I plus j. Now you need its norm. This is the square root of 1 squared plus 1 squared. We get the square root of 2. So you're looking for this. You're looking for this line integral of x squared plus y squared ds. So this is the line integral. So t is going from 0 to 1. 0 less than or equal to t less than or equal to 1. Right? So this is the integral from 0 to 1. X squared plus y squared. Where here x squared will be t squared plus y squared. Well, y is equal to t, so this is t squared. Then it's times the norm, because the norm times dt represents ds. So this is the square root of 2 dt. So this is 2 times the square root of 2 times integral from 0 to 1 of t squared dt. I just got through eating lunch, and so I'm just out of it. Got these wings from this Gridiron Grill place in Decatur. They were really good. The lemon pepper and the Jamaican jerk and the collard greens. Oh my goodness. And sweet tea and water. I don't feel so well. But anyway, let's integrate 2 times the square root of 2 this becomes t to the third over 3. We evaluate the t from 0 to 1. And so we just end up with 2 times the square root of 2 all over 3. All right. Here, the path is moving counterclockwise, counterclockwise around the circle x squared plus y squared. And you're going from 1, 0 to 0, 1. Well, think about this in terms of t. Here is going from 0 to pi over 2. And using polar coordinates, we can represent x here. This has a radius of 1 because of how this circle is defined. So x is equal to r cosine theta, what we use in t. I know this is 2 variables, but r is going to be fixed. So this is r cosine t. Then y is equal to r sine t. So here, x becomes cosine t because r is equal to 1 and y is equal to sine t. Now, I say r here, I'm talking about just the radius for the circle. So I'm not talking about r of t being defined as the position or the path vector. Right? So this r may be misleading. It's the radius. So here again, this is just the radius. So this is not the path vector. R of t is. So here R of t is equal to cosine ti plus sine tj. So R prime of t is equal to negative sine t plus, there's an I there, minus cosine tj. Now, what's the norm of that? It's going to be 1, right? So the norm of R prime of t is equal to 1. So we have that. I think we're ready to work. Now again, what's the function? Well, problems 11 to 14, the function is x squared plus y squared. So for this problem, you're looking for the line integral of x squared plus y squared ds, which becomes, look, t is going from 0 to pi over 2. 0 less than or equal to t less than or equal to pi over 2. So this is the integral from 0 to pi over 2. X squared plus y squared, where x is cosine, so this is cosine squared t, plus y squared, that's sine squared t, and it's times the norm of r prime, which is 1, and that's times dt. Well, this is just the integral from, well, it's supposed to be the integral from 0 to pi over 2 dt. You see that the answer is just pi over 2, right? This is t evaluated from 0 to pi over 2. And all we have left is just pi over 2. Here, find the parameterization of the path C, and then part B, evaluate. Here you're along the x-axis where x goes from 0 to 1. So R of t is equal to ti plus 0j. Along the x-axis, that's letting us know here that y is equal to 0. So this is just ti here where t goes from 0 to 1. Well, that works out pretty good for us. So we have this line integral of x plus 4 times the square root of y ds. This is the line integral from 0 to 1. Oh, what's r prime of t? That's equal to I, and its norm is just equal to 1. So here we have the integral of x. X here is t, and this is plus 4 times the square root of y, but y is 0. This is times the norm, which is 1 times dt. This is just the integral from 0 to 1 of t dt. And that gives us t squared over 2. That's evaluated from 0 to 1. So all we have here is just 1/2. Well, what if you have the line integral and you want to find it using vector form, or here some type of differential? I think what's helpful, we're trying to calculate here this capital F vector field, dot product of that with the tangent vector ds, and that's what the line integral materializes itself into being. Now this tangent vector here is r prime divided by the norm of r prime. You recall that from chapter 12. And then ds is the norm of r prime dt. Well, the norms cancel, and so all you have left is the dot product of f with r prime t dt. And so that gives us here the line integral itself, the dot product of f with dr. So this is the line integral in differential form. So we use that here to work. Let's work this problem. So this is the same as the line integral over f of f dot. Again, dr is r prime of t dt. Now this is different from here, the so-called line integral of f of xy, or f of xyz ds, right? We're calculating the same thing, but we're going at it in a different fashion. So here we need r prime of t, and so r prime of t is I plus j. And you relate the function with r prime. I need to take a break. Okay, I think we're back. Alrighty, let's see. So that was r prime of t. Now notice that the function f, which is equal to xi plus yj, but what is x and what is y? Well, I tell you that x is equal to t, and here y is equal to t, right? So if that's the case, you see here that this x is that t and this y is t. So this is actually ti plus tj. So this line integral over the curve of f dot dr is the integral from 0 to 1. Here the function f is ti plus tj. This dot product with dr, excuse me, and dr is r prime of t dt. Well, r prime of t is at I plus j, and then here this is dt. This is the integral from 0 to 1. To the dot product, all we have here is t plus t dt. This gives us 2 times the integral from 0 to 1 of t squared dt. You integrate that, we get 2t squared all over 2. Evaluate that from 0 to 1, and that just gives us 1. Well, one more here in this section. So do you see that the function is 3 times x? What is x? Cosine ti plus 4 sine tj, right? X is cosine t and y is equal to sine t. So the function f in terms of t is 3 times x, but x is cosine ti plus 4 times y, and y is sine tj. And we have r, we need r prime of t. That's negative sine ti, and r here, plus cosine tj. So to find this line integral of f dot dr, this is the integral from 0 to power over 2. The function f in terms of t is 3 cosine ti plus 4 sine tj. That's dot product with r prime of t dt. This is negative sine ti plus cosine tj. This is dt. So we do the dot product, do the hokey pokey, and you turn yourself around. This is negative 3 cosine t sine t plus 4 cosine t sine t. This is dt. So this is the integral from 0 to power over 2 of cosine t sine t dt. Let u equal to sine t. So du picks up the cosine t. Cosine t dt. So here we have the integral from 0 to power over 2. This is just u du. So that gives us u squared over 2 evaluated from 0 to power over 2. But u is the sine squared t all over 2 evaluated from 0 to power over 2. So sine of power over 2 is 1. So sine t here at power over 2 is 1 squared. So it's just 1 divided by 2. And all we have there is 1/2. And we should be good to go, I think, on all of that. Looks good to me. Well, I'll stop there. Thank you.